Hi everybody, my name is Xuefeng Luo from SFS, University of Tübingen in Germany. This project is worked collaboratively with my supervisors, Dr. Yuying Chuang and Professor Harold Bai. Today, I will talk about the new implementation in Julia, JudiLing, of our LDL model. It works well and super fast compared to our R model. So first thing first, what is LDL? LDL, linear discriminative learning, is a two-layer network language model. It tries to model the comprehension and production of human beings. Talking about language models, there are already plenty of deep learning neural network models available. They are great. They did really great jobs. However, when we have hidden layers behind hidden layers, we lose track of those machines. We don't know how exactly those machines work. And they use a lot of energy during training. Therefore, we want to build a new network model as simple as possible in a higher dimension without any hidden layers. Since we don't have any hidden layers, this model becomes transparent, and it is interpretable compared to deep learning neural networks. Then we want to see how far we can go with this model. We had already implemented our model in R, WPM with LDL package. One nice thing I can tell you about it is it works. And this model has been applied to a variety of studies, such as morphologically complex words. Other studies like auditory comprehension, speech production, etc. We conceptually proved a model works, but since we didn't optimize our model in R, it has bottlenecks when we scale up to a larger dataset. Once we had trained our French dataset over 21,000 phrases, it took 8 hours and then crashed because it used too many memories. This was the moment that we had an idea to upgrade our package so that it can scale up to a larger dataset like French or even larger datasets. Before we jump into our model, I want to introduce Julia to you first. So Julia is a very fresh programming language. It starts in 2012 and released its 1.0 version only 2 years ago. Currently, it is under 1.5.2. Even though it is a new programming language, it grows rapidly because there are not many programming languages that can be both fast and easy to use. You will see how fast it is when I talked about those bottlenecks. So back into our model. Our model is a simple two-layer network model without any hidden layers. The underlying mathematical mechanisms is pretty much the same as multivariate multiple regression. What we had is two numerate vector representations, C for word forms and S for word meanings. And what we are interested is two direction mappings between C and S, the F and G. To get those mappings, we relied on the matrix inversions highlighted in the equations. In this example, you see the matrices are very simple, but in real world, matrix inversions are going to be very expensive to compute, especially for R. This brings us to the first bottleneck, where we relied on computing inversion for matrices heavily. Here I attached a graph comparing processing time for matrix inversion in Julia and in R. The x-axis indicates the size of the matrix, and the y-axis indicates how long it takes to find the inverse of that matrix in seconds. Please notice that the time is in the base of log 10. As you can see with the red line and the blue line, the generalized inverse or pseudo-inverse in R is quite expensive, but in Julia it takes less than 2 minutes. The green line shows the actual algorithm used in our package for matrix inversion, the Cholesky decomposition. This algorithm further reduces processing time to around 10 seconds. Imagine a process used to take 30 minutes to process, and now it only takes 10 seconds. How fast it is. Back into our model again. When we model the comprehension, the mapping is not always perfect. Therefore, we need to calculate all correlations between word predicted semantic vector and or golden standard semantic vectors, and then select their closest neighbor. As you can see in the example, the predicted S hat cat is not exactly the same as S hat, but it is the closest neighbor. In this situation, we need to calculate correlations a lot. This brings us to the second bottleneck of our R implementation. This graph shows the time difference of calculating correlations between word predicted semantic vectors and or golden standard vectors. The x-axis is the number of words. If there are 2,000 words, then there are 2,000 times 2,000, which is 4 million correlations we need to calculate. On the production side, the first step is similar to comprehension, but what we had is the semantic vector scat, and what we multiplied s hat cat with g, we can get the predicted c hat cat, so that it shows which trigrams are present in the word cat. However, when and where should we put those trigrams? You probably also find out that those trigrams themselves implicitly indicate that if they had overlay in between, then they can link up to a path. Yes, this is the way we use to build the path. So this is the graph shows an algorithm which we originally implemented in R. We used a graph-based algorithm to find all possible paths among those trigrams, and we select the best supported path as the prediction. However, this algorithm doesn't work well when we scale up to a larger dataset, because the number of paths increases exponentially as the number of the trigrams increases. So we developed a new algorithm. This algorithm not only predicts which trigrams are in the words, but also predicts which trigrams are in which positions. For example, for time step 1, the model learns that #CA and #SH are most likely to be in the first position, because they have starting word boundaries. Similarly, for time step 2, the word model predicts CAT, SHI, and CAP. Then we can link all possible trigrams to form a path. The same as time step 2, we had predictions for time step 3, but in this time step, we already have paths containing the end of the word boundaries. Therefore, we store those completed paths in a list separately and no longer track them anymore. For time step 4, we had another path completed. But for path SHIPP, since it is not completed, we drop it at the end of the algorithm. Finally, we evaluate all of the candidate paths and select the best supported prediction path. Compared to the old algorithm, our new algorithm restricts trigrams in each time steps. Therefore, we don't have paths that increased exponentially. This graph shows the processing time for those two algorithms. The process used to take almost 1 hour, but now it only takes within 2 minutes. We had for JudiLing better algorithms for inverting matrices, calculating correlations, and finding paths. Those better algorithms make the model now use much less time to process and support for larger datasets. JudiLing is now available online on GitHub. If you are interested, you can go there and find it documented in detail. This brings the end of my presentation. Thank you all for your attention. Do you have any questions?